Well, thank you, Rob and Julia, for the invitation. It's a pleasure to be here. It's nice to give a talk in a place I don't have to travel to get to. And, so the talk's going to be about coalescing random walks, but I want to start with a different model, which we'll see is very much related to, coalescing random walks. But the model is over here. So this is a realization of what's called the Watt-Strogatz model for large networks. Some of you might have heard about small world networks, so that's sort of the small world model. So you have a cycle, and you add edges randomly between some of the pairs of vertices. They're not connected originally in the cycle, or something like that. No? What's the definition? Oh yeah. So okay, I guess I'm starting with the power, the first power of the cycle, and then I'm adding edges.
You can't rearrange the edges. They deleted and rearranged.
Yeah. So maybe the people who wrote this applet defined it wrongly. So it's I'm following their definition. So it's a kind of modified Watt-Strogatz model. Okay, and the voter model is like this. So you see that each vertex has a color here, and the color corresponds to an opinion, say. So each vertex has a clock, and when the clock rings, it picks a neighbor uniformly at random from the set of neighbors, and it switches its own color to that neighbor's color, right? So it changes its opinion according to the neighbor it's picked. So when the model evolves, it looks like this. And let me say the first theorem, which is very easy to prove about this model, which is that it always achieves, with the graphs connected, you will achieve consensus in finite time, meaning that there's a finite time after which everybody will have the same color, right? And that's not hard to prove. I mean, with some positive probability, that will happen at some time interval, some amount of time interval. So it just keeps repeating, right? And you see, I guess that red has already disappeared. So now there are only two opinions left, right there. Now let's leave this thing running. So maybe for a slightly more formal definition, you have the graph here. I only have two opinions to start with. And, each, just to be very formal, this clock process for each vertex is a Poisson process with some rate, say rate 1. And then when this vertex rings, it picks a neighbor uniformly random and changes its color, right? So, this is a very well-known model for people who do interacting particle systems. It's usually studied over infinite graphs, or more specifically, the infinite lattice. But today I want to say something non-trivial about the finite case. So we know that consensus is achieved, but we want to know how long that takes, or what's the distribution of that time. And, as it turns out, you can map this to the problem in the title of the talk, which is coalescing random walks. And here's how you do it. So here you have arranged the vertex of the graph, just on line, but just for convenience, to make the drawing easier, right? And the arrows represent the times at which a vertex decides to look at a neighbor to switch its opinion to that neighbor's opinion, right? And now let's say you have this, where is the button here? Hopefully, okay, good. Let's say you want to find out what's the opinion of this guy at this time, right? So what you do is you go backwards in time. Well, here's the last time it looked at someone else to change its opinion. So its opinion here is the same as this guy's opinion here. And you keep on going. So this is the last time this guy changed its opinion. So you look, and you go down, and you look, and you see black here, which is why this is black, right? So if you follow this trajectory backwards in time, it turns out that you have a random walk on the graph, a continuous time random walk, meaning that you move at the times when a Poisson process rings, right? And when you move, you pick a neighbor uniformly at random, you jump there. So that's the process you see for one of these guys. What's interesting, though, is that when you have more than one, the walks are coalescing. So if you look individually at this node, you also see a random walk going backwards in time. But if you look at two of them, you see that from this point on, no matter what happens, they'll have the same opinion at this time, right? And when you look at all nodes at once, you see, in this case, you have two coalesced clusters. These three oh, actually, yeah, these three and the one over here, they have all coalesced by time 0. And, well, time's going backwards here, right? And you have these two that have also coalesced here. So it turns out that the consensus time in the voter model is related to the time it takes for random walks to coalesce. Well, you don't really need all the random walks to coalesce into one single random walk to have consensus. Say, if these two happen to be black, you would have reached consensus by this time, right? But, well, for simplicity, just to make our life simpler, we're going to imagine that all of the initial opinions are different, which means that in order to have consensus, you really need to see all random walks coalescing into one single random walk, right? So that's the random variable we're going to study here. And well, when I write that voter model is dual coalescing random walks, I just mean this thing, right? So I don't want to be too formal about what duality means. Just want to say, well, voter model backwards in time equals coalescing random walks. And the goal is to understand this first time at which all the random walks are coalesced into one. As I said, that's, of course, that's assuming all the initial opinions are different. It's not hard to use the same ideas I'm going to present here to understand the case where all the initial opinions are IID, say. Okay, so it's really a minor extension of the analysis I'm going to sketch here today. And, well, maybe I want to switch to the... No, okay, there's I guess the result stated here. So just to jump ahead to the solution, what's this going to look like, right? So, and it's a very loose statement of the solution, so we're going to try to be more formal and more precise as we go on. The very informal statement is, if you have a large graph, well, I guess I use the word network here just to try to be cool, but it's a graph. If you have a large graph with a small mixing time, and I'm going to define what a mixing time is later, the distribution of this consensus time rescaled by some factor, which I'm going to explain pretty soon, is essentially the same as in a large complete graph. So that's where the mean field comes from. So mean field means for me a model with geometry, so the complete graph. And moreover, the expected value of this consensus time is twice this mu sub g, so I'd better say what mu sub g is. Well, this is the expected meeting time of two random walks in G. Right, so I'm saying this. So you have a system of potentially, 1 trillion random walks on your graph, and as long as your graph is reasonable in some sense, the time it takes for all of them to coalesce into one cluster is twice, well, the expected time, that is twice the expected time for a pair of particles to coalesce into one cluster.
What does C depend?
So C is the coalescence time for a given graph. Right, so you have, I'm saying, take a large graph, a large G with some reasonable structure, which I'm going to define later, and then you have this kind of result, right? So, and yeah, but I'm going to be a lot more precise about what I mean by this, and there are actually different sets of conditions on G. So, well, let me maybe switch now to the blackboard, and yeah, except that I want to leave this on. Pode desligar aqui. So what I'm going to do now is to state a very precise result about what I mean by this. And well, so here's a, can you all read this? Can you see there's a T and an H here? Okay, good. Okay, so to make things simple, at least okay, as we start here, I'm going to state a result for vertex transitive graphs. And then I'm going to try to explain why this is interesting. But so well, say you have a vertex transitive graph. Let me define that parameter mu sub g, expected meeting time of two random walks starting from the stationary distribution, which in this case is uniform, right? So pick two vertices in your graph uniformly at random, start a random walk from each, look how long it takes for them to meet, and it takes the expected value. That's a parameter here. And C is what I call the full coalescence time. And, well, I guess that to be extra formal here, I'd have to, well, okay, I'd have to have a parameter here that tells you they actually have a sequence of graphs, right? And the theorem is that and now I'm actually going to write, so this is reconvergence. And I'm going to write down the explicit form of the distribution of the limit. Oh, sorry. And yeah, there's something else I must add here. Okay. Another parameter here. T mix. I'm going to say later what the mixing time is for people who don't know. But and then if the ratio of the mixing time to this parameter here goes to 0, as n goes to infinity, then the ratio, well, this random variable divided by this scaling factor, it's going to converge as n goes to infinity to something with a very explicit form, though it's a bit funny the first time you see it. So the terms, you have a sum of random variables, an infinite sum, and the terms in the sum are exponential random variables with parameters I choose 2, and all independent. Okay, I'm not trying to convince you that this makes sense now, but it's just for a reality check. If you look at the expected value of this, you get a sum of inverse binomial coefficients, and that's going to give you a 2 in this case. I mean, that's an exercise. So as it turns out, we're going to prove this convergence in what's called Wasserstein distance. Well, for people who know what that is, which means that the expected value of this does converge to the expected value of the sum. Okay? So, what? What's that? L1, yeah. Yes. And yeah, so that's one result that's going to come out of the analysis. And later on, I'm going to state some results for non-transitive graphs, and unfortunately, the conditions are not as sharp as this one. But well, as you're going to see, the results are still interesting for some certain classes of models. So maybe let me say a bit about the history of this model, about the history of this problem. So. So the computation, as I said, I mean, this is the same limit as you have for the complete graph. And I mean, it's not hard to show that the complete graph actually satisfies these conditions. But for the complete graph, you have a very explicit calculation. Right? So the complete graph is sort of folklore. But for people who are interested in such things, let me say that this is somehow related to Kinman's coalescing. Then you have a case where that was studied by Cox, actually in the context of the voter model, but right, which is, so this is a discrete torus, large discrete torus with fixed dimension. So for d bigger than 1 or larger than or equal to 2, you have this mean field. What mean field for me means this limit, right? And that's due to, well, and also for d equals 1, you don't have mean field. And that's due to Cox. I think, 87. I always forget the years of papers I cite. But yes?
What are these T-mix and mu for these models? So just
yeah, so that's what I'm going to say right now, right? So, well, complete graph, you have T mix equals big O of 1. And mu sub gn equals n minus 1 over 2. So, yeah, clearly satisfies the conditions, right? So, for d equals 1, you actually have that mu sub g and the t mix are both of the order n squared, right? So, n is the length of the torus, right? So, it clearly violates the conditions of the theorem. Here, you have that t mix, well, it's always of the order n squared. And mu sub g is of the order n squared log n for d equals 2, and n d for d bigger than 2. So also satisfies conditions. I mean, this sort of, the d equals 2 case barely satisfies the conditions in some sense, right? Because you have this logarithmic, inverse logarithmic ratio. But it's, so, and well, there are more recent results which I guess are the only results known for non-transitive graphs, which are due to Cooper, Fries, and Rajcik. And that's a 2007 for, well, expander graphs. Satisfying some non-standard, well, I mean, not just an expander. You need an expander with extra conditions. So, well, let me say a random regular graph. So typically, a random regular graph is mean field in this sense.
Just GNP?
No, GNP, I guess...
When you say random regular graph, which model do you mean?
I mean the configuration model for a fixed degree, right? I mean, since the degree is fixed, it's just, the same as for any other model. But I guess, I mean, if you look at their analysis, I guess you could extend it. Well, I can certainly extend it, but even their analysis could be extended to increasing degree under the configuration model, because they just have a finite set of conditions that you need to check in order for the graph to be mean field, which is why I didn't want to start with a random regular graph. I mean, it's an expander satisfying some extra conditions. So.
That's also mean field.
What do you mean?
Same phenomenon happens for random regular as for a complete graph.
Yes. Yeah, so yeah, you really expect to see mean field behavior for all degrees, right? And that actually comes out of this analysis, so as you're going to see. Because, I mean, what we're going to see, even in the case of non-transitive graphs, essentially the condition you get here is T mix divided by the number of vertices goes to 0. For regular graphs, that's enough to prove mean field. So, and since the mixing time is always small, so you know that you do have mean field behavior, right? But, well, since I mentioned this, let me also add that here, if you only looked at the number, so you have T mix divided by the number of vertices, that wouldn't work for dimension 2 here. Right? So it's important to have T mix divided by this mu. But that's a bit too technical, perhaps, to insist on right now. But, yeah, so those are essentially the only results. Well, there's a problem that was posed by Aldous and Phil, which is that, and I guess I'm going to have to erase this pretty soon, but which is, well, for G vertex transitive, their problem was, is it true that, you can if the ratio of the relaxation time, relaxation time is just the inverse of the spectral gap, for people who know what the spectral gap is. Is it true that the relaxation time divided by mu going to 0 implies mean field? And as you can see, that sort of, it's well known that mixing times and relaxation times are of the same order for these It's all right. So that I think was their inspiration for the problem. So I can't really prove that. But since this thing here is always at most of the order of the mixing time times log of the number of vertices, right? So it does get pretty close to their conjecture, and still it's a generalization of Cox's result in any case. Right? So, let me just emphasize. This is a question, right? This is a problem, which hasn't been solved so far, at least to the best of my knowledge. So I have more than half an hour left, so I'll try to, first of all, to explain to you the analysis, or the main parts of the analysis. And then I'm going to try to explain what needs to be modified in order to make things work for other graphs, not necessarily vertex transitive. And why do we lose something in the analysis when we move to non-transitive graphs, right? As we're going to see, essentially all the pieces of this analysis were known before. It was just a matter of putting them together, and maybe with minor tweaks, which actually happen to be essential, right? Well, but before I actually get to the analysis, let me just try to explain where this formula comes from, right? And for that, I really want to do the complete graph case. So, yeah, I guess I'll need to erase something here. Yes? L1. Well, I could do L2, LP for any fixed P. But it's L1 is more convenient sometimes to work with, and for this problem at least. And but as I mentioned this as if it was kind of a minor issue, but it does happen to be important in the analysis that you get those things not for just regular weak convergence, but somehow it's easier to do induction, as we're going to do here, with Wasserstein than with other metrics. Right, so maybe I want to sketch the computation of the full coalescence time on the complete graph, so they understand where these exponentials are coming from. And I guess I'll have to erase this, but, well. So the complete graph case, of course, it's very simple because it's got lots of symmetries, right? And the critical part of the analysis is understanding what happens when you move. Say you have k particles here, and you want to move to k minus 1 particles here. Right? So, the full coalescence process is a sequence of things like this. Right? And, as we're in the complete graph again, right? So, and by complete graph, I really mean that you jump from the random walk on the complete graph is jump from either j at rate 1 over n minus 1, which means, just what I described before, right? So you have a Poisson process with rate 1, and then you choose one of your n minus 1 neighbors uniformly at random, you jump there. Right? So the main point is this. So these particles are evolving. But whatever happens that is not a coalescence doesn't really matter in the sense. Because if this guy moves to another vertex, well, the complete graph is really symmetric, right? So it doesn't matter what this guy is. It only matters if it jumped on top of one of the existing particles or that it didn't, right? And then, well, we need to compute the rate at which one of these guys will jump on top of another. Right? And well, here's what it looks like. So you have here, you have k choose 2 pairs of particles. And for each pair, you're going to see a coalescence at rate twice this, right? Because one guy may jump, a guy A might jump to B, or B might jump to A. And you're waiting for an event that's going to happen at this rate, or k choose 2 independent events that are going to happen at this rate. The independence really comes from the symmetries of the graph, right? So this is going to give you a time that's, that's going to be an exponential with a rate that's this times this. And this is already quite similar to the random variables I had precisely over there before, except that there is this extra n minus 1 over 2 here. But, well, as I already wrote over there, in this case, mu sub gn is n minus 1 over 2. So when you divide by the scaling factor, you really get this, well, this, so this time here you could say that, well, tau k, tau sub k is n minus 1 choose 2 times exponential with, well, let me write with mean k choose 1 over k choose 2. So this is what it looks like, right? And the analysis essentially consists of taking this statement and proving that is in some sense true for any graph. But there are several issues with this idea, right? So let's try to enumerate them. So, well, when you want to prove that a random variable is exponential with a certain mean, you first have to prove that it's exponential, and then have to prove that it's got the mean you want to have, right? But there are a few things, right? So, well, so there is a very well-known general principle for proving that hitting times of sets or Markov chains are exponential, right? And this, well, let me just emphasize: you have k random walks. And if you look at them collectively, you have one single random walk, one single Markov chain on a Cartesian product, right? And here you have, let me just write this. You're looking at the hitting time of a set that I'm going to write down k, which is a set of all vectors of vertex raised to k, where you have two coordinates that are equal. Right, so the things you're trying to look is you have these, as I said, you have, okay, the Markov chain is just k random walks on Gn, or G, maybe let me forget about the index n. So in general, we're going to look at something like this, to look at the time it takes you to move from k particles to k minus 1. We have k random walks. Look at them all together. That's one single Markov chain. And we are looking at a hitting time of a set here. So what's the first time at which this set of k random walks enters this set? Well, this ensemble of random walks enters this set, right? And then there's a general question: what's the distribution of the hitting time of a set by a Markov chain, right? So here's a general principle. So maybe I should define finally what a mixing time is, because I'm going to need that. So let's say I have a Markov chain or a random walk on a certain certain state space S. Let's say S finite. And when I write things like this, P sub x, x sub t belonging to A, this means that the random walk started from x, right? People not everybody might use this notation. And then as it happens, if you look at, say, random walks, this kind of continuous time random walk on a connected graph, you always have this loss of memory property, which means that you look at any two starting points, you look at any subset of states, And the probability that, so you might ask, well, what's the probability that the random walk started from x happens to be at a at time t? And then the same for the random walk started from y. And as it turns out, well, with other kind of very minor conditions, this goes to 0. Meaning that the distribution of the random walk asymptotically is independent from the initial state. Right? And the mixing time is just a way to quantify this. So maybe I'm going to write over here. T mix, so is the least t such that that maximum that I just wrote, well, T mix epsilon, there's least time where you have that maximum I wrote over there. Smaller than epsilon, smaller than or equal to epsilon. Right? So that's the mixing time. And usually when we write T mix, we mean T mix 1/2 or 1/4, I don't know, let's say 1/2. Here. Right. Well, since while we're at it, let me just define the stationary distribution. And the stationary distribution is just this. Well, I mean, it's both stationary and the asymptotic distribution for this process. It just means that this is the limit as t goes to infinity of p sub x, xt belonging to a. As we saw, this limit's not going to depend on x. And as it turns out, if you pick your initial x randomly according to this distribution, at any given time you'll still have this distribution, right? So I'm sure most of you have seen this before, but just want to be, I mean, if anybody has questions right now, please feel free to ask. Right, so, well, now that we know what a mixing time is, so I can discuss my general principle, and maybe I'll put it over. Okay, I wrote general principle over there, but I'm going to actually say what the general principle is over here. The general principle is this. So let's say that you have a subset of your state space, which is small, meaning that the mixing time is much, much smaller than the expected time it takes you. Okay, let me say hitting time of A is just the smallest t such that you belong to A. And let's say that the set is so small that the time it takes you to lose memory of your initial state, it's much smaller than the time it takes you on average to get to that set. Right? So in this case, you expect to see, well, and that's actually a general result. And, well, maybe I'll have to define this. You expect that this hitting time has a distribution that's approximately exponential with this expected value. So this is the general principle. And I mean, it's not only a principle, it's a theorem, right? So it's not, there are various versions of this due to Aldous and Brown, and I guess a bunch of others. But I'll mostly be interested in quantitative versions where you have control what's happening over here. And so, yeah, and we're certainly going to use that in our analysis to say that the hitting time of this set is exponentially distributed, at least if k is not too large. If k is large, then you have to do something else, right? But there are problems with this idea, and then let me say what the problems are. So I want to prove that the hitting time of this sort of pretty much a diagonal set is exponentially distributed, right? So as I said, you need k k cannot be too large here for this work, but that's not a big issue. What is a big issue is that if you're not in a complete graph, but rather in an arbitrary graph, then, well, we still don't know what this is. Of course, that's going to work in the end, but, well, we do need a little bit of suspense. And so mu sub gn is a parameter, so we have two problems here. But first of all, when we move from k to k minus 1, we're not going to start from the stationary distribution, right? So k is the number of particles we have after a long time in which this process has been evolving. So we're not, I mean, as it stands, this kind of principle is not quite applicable to our situation. So this is difficulty number 1. And difficulty number 2 is related to that. How do we know that the hitting time of this set here, or the expected meeting time, is what you need it to be, which is this. I mean, we need this in order to prove that we still have something of this sort, right? We're replacing, so we don't have a rate now. We need this to be something like, yeah, for everything to work. Right? So there are two difficulties in them, and I'm going to try to sketch. I mean, it's actually not there are difficulties, but they're not such big difficulties as we're going to see. It's just a matter of looking at what people did before and seeing where, kind of finding the right spots in their analysis and seeing what happens. So maybe I'll discuss this difficulty first, since it's kind of, I guess, in some sense it is the kind of the main new thing in the proof, I guess. And yeah. What was that? So mu gn is the expected meeting time of two random walks. So as you see, here you have, I mean, you can more or less guess where this can come from, right? So you have k particles, you have k choose 2 events. The meeting of any two of these particles should take time of exponential with this mean. And you want to prove that if you look at all of the meeting times, they sort of behave as if they were independent. So that's what I'm going to say right now, right? So, well, let me rewrite what I just said. Here's a well-known, very basic result. Let's say you have independent, well, maybe not xi, wi, independent random variables, and each one of them is exponential with mean mu. Well, maybe since independence, right? So the IID exponential is with mean mu. What's the distribution of their minimum? Well, the probability that the minimum is larger than t is a product of these things, right? Well, if the minimum is larger than t, is because each random variable is, well, the minimum is larger than t, rather, is because each one of those is larger than t. So, of course, you have a power here. And the important thing is that the minimum, let me write it, is exponential with mean mu divided by m. And again, right? Here I have k particles, k choose 2 events, right? The time for each one of those events, well, if you sort of believe this general principle, right? The time for, well, you look at a pair of particles, you have a meeting time of 2 particles. So expect to have the exponential with this mean. Now we want to prove that the mean, when you look at all those k choose 2 variables, is the original mean divided by k choose 2. So we expect, I mean, and this, if we could show that the individual meeting times are independent, would be all done here. But of course we cannot, right? So it's, well, kind of the analogy here, which is very imperfect, is that, so these are the pairwise meeting times. Right? And then each wi should be approximately exponential with mean mu sub gn. And we'd like to conclude that the minimum is exponential with mean mu sub gn k choose 2. But as I said, I mean, we don't really have independence, so we can. It's not that easy, right? Yeah. So, well, I mean, the issue in some sense is that let's say you look at a kind of reasonably large, but not too large time interval. So there's some probability that you see a collision, you see a meeting, and there's some probability that you don't. And somehow you want to say that pretty soon after that, they will look again as if they had started from the original distribution. Right? And actually, I'm going to kind of say what we need to prove in order to do this. Right? So, and it's again, it's a kind of a new general principle in some sense. But let me. So it's a general setup for. You have M sets contained in the state space. So again, we're going back to that general setup markup chains. You have a set that's the union of them. Right? So here we have like the sets would be, well, the sets of vectors of length k where two coordinates coincide. And A is the union, is that delta sub k here. Right? So now, well, we expect all of these times to be approximately exponential, right? So let me write this in a different way. Well, let me also say that the hitting time of A is the minimum of the hitting times of the AI, right? A is the union, right? So the first time you hit A is the first time you hit one of these sets, A1 through AN. So we really expect a formula like this to hold, right? Oh, sorry, 1 minus for each one of these. And here's the key idea. It's that, well, if t is small, let's say, well, t equals epsilon is very small. So you have the probability of h sub b smaller than epsilon, hb. This should be about epsilon. So the quantile, the epsilon quantile of the distribution is approximately epsilon times expected value. Well, what about this? And now again have to move to the other side, I guess. Though, yeah, well. So the point is that the quantiles of the meeting time of the union and of the meeting time of the individual sets are related, right? So, well, here I'm assuming, let's say that the h sub I all have expectation mu. H sub AI, expectation mu. Just to make life easier. Right, so, yeah. So using this general idea, if you sort of believe that everything's going to work out at the end, what you do is this. So what's the probability that H sub A, the union, that is smaller than epsilon times, well, not its own expected value, but mu. Right? Well, this is the probability of H sub A being smaller than epsilon times mu times its own expected value times the expected value. Right? Haven't done anything so far. But then we said, well, if this is small, what the probability you get should be precisely this number. And now the key point, which you need to prove in each individual case. And of course I have stationary distribution over here. Now this is really the key point. You can look at this event. Well, it's a union of events, right? So it's the probability of union over I equals 1 to m of h sub ai smaller than epsilon m. Now, if you can prove that the probability of the union is about the sum of the probabilities, and that's, well, that's a big if, but sometimes you can prove this. You have something like this. And again, this is a big if. I mean, I'm not saying this is obvious. What we should prove is that the correlations between these events are small. Right? Because now what you have, well, each one of these probabilities should be epsilon, right, by this idea over there. So you have epsilon times m. And you compare these formulas. I mean, here I have the same probability written two different ways. And what comes out of this, plus this, is that you really should have, well, you just see, here you have mu, well, this expected value divided by mu should be like 1 over m. So it's really what we want here. Right? So everything, I mean, of course I'm being very informal here, but everything sort of hinges on one such calculation. And what do you need to do to prove this? Well, I already said it. You need to prove that correlations are small. So, and let me... So let me... M is like case choose 2. You know? Okay. Yeah. So maybe I should write this over here. Well, because they're the pairwise meeting times, right? And that's really what makes it difficult, right? So if the events they're looking at happen to depend only on each single random walk, they're independent by definition, right? So everything would be easy in that case. So, right, so now what do you need to prove to make this work, right? So this is sort of the sticking point. And the point is this. So this works if the sum of these probabilities if this sum happens to be of the order of epsilon squared times m squared. Well, look, each one of those events, this should have probability epsilon. This too. If the correlations are small, you expect the probability of the intersection to be about the product, right? So you have epsilon squared. And you have m choose 2 terms here. Right? So essentially you want, okay, perhaps it's even better to write it like this. So just to make it easier to see. Right? So if you have this, then you can prove that the probability of the union is about the sum of the probabilities, and then you're all set. And how? Well, so now let's talk about a specific case. We have meeting times, right? Again, the random variables are the pairwise meeting times, and you want to see what's the probability, say, that you have, let me see if you can understand this, probability that 1 and 2 meet before time epsilon times mu, and then 2 and 3 meet before this time. Yes?
That seems weaker than I was expecting. Why can you use a constant?
Well, because in the end you're going to use something like a Ferroni inequality, like inclusion, exclusion up to term 2, right? So, well, on one side this is certainly smaller than this, right? On the other side, this is larger than this minus the sum of terms of this form.
Because epsilon is small.
Yeah, because epsilon is small. So you need epsilon to be very small relative to m as well, right? So it's epsilon should really be small. You know? And that in some sense is implicit over here because, well, anyway, yeah, that's the reason. So in the end, what you need to do is to compute probability like this. And let me show you why this is easy on a transitive graph, right? So let's say that you have, well, random walk number 1, random walk number 2, and then random walk number 3. And let's say that you're looking at an event where where 1 and 2 first meet, and then 3 meets 2, right? In this time interval, which is like epsilon mu. Right? So you could have another event where this meeting happens before this one, but this is half of the probability, right? So what happens here? Well, the point is, there's a probability of meeting here, and this probability is about epsilon. Now, by the Markov property, you have, well, look that this guy here is independent from this meeting, right? So 3 is uniform here, so it's stationary here. And whereas this guy, well, the graph is vertex transitive, right? So this meeting time is also uniformly distributed. So this is also stationary. And now you have a time left here that's at most epsilon times mu. So essentially you're asking for the same event to happen twice. Right? Can you see the idea? It's just that, well, even though you had a collision, even though these two are dependent, they're not quite dependent because you have 1 and 2 meet, so you're stationary here. And then, well, since you're also stationary here, it's the same thing again. Right? So this probability here really is epsilon squared, or actually can make this formula, it's less than twice epsilon squared if G is vertex transitive. So, well, I mean, there are other difficulties, of course. First of all, you're not, as I said before, you're not really starting from the stationary distribution at any given time. So you need to say that, in some sense, that exponential approximation is still valid if you don't start too close to the set you want to hit. Right? And that requires some work, but it's I mean, I've never seen another paper. I'm sure that someone must have done this before. So I don't know. Whereas this really seems to be new, even though it's simple. So yeah, there's this issue of non-stationarity, which is you can deal with very easily. Well, the induction gets kind of boring, but you know. There's this issue of correlations when the graph is not vertex transitive, and that I don't really want to get into, but you can still have bounds. Not as good as this one, but you can still have bounds and correlations. And the third issue is what you do with very large k. Because in the beginning of the process, you really don't expect exponential approximation. So at any given time, anyone might bump into anyone else. So, well, for the complete graph, yes, things are exponential from the outside, but not in this case. And then you need a separate argument to tell you what happens there. But let me say something simple, which I mean is actually the best I can do for for general graphs, which is this. So say you have many, well, the first thing is that the exponential approximation is always an upper bound. So if k not too large, the probability, this from any initial state, the probability that the first meeting time on k particles is larger than t, this is going to be less than constant, t constant, mu sub g, well, there's a k choose 2 somewhere. So if you use this, so any of the n choose k sets of k particles in the beginning of the process, we'll see a collision by a time, well, you want n choose k times this to be small. And then you have to see how large you need t to be. And it turns out that's going to be mu sub g log of n divided by k. So all I mean by this is, in order to take care of the initial phase of the process, you need to prove inequalities of the kind we want, for k of the a bit larger than log n, so that you can get rid of this time. Say that, well, the beginning of the process is so fast that you actually pretty much don't see it happening in some sense. And from then on, you use the kind of argument I presented. And, well, I guess I'm pretty much out of time now, so I'll stop here. And thank you very much.